Hi everyone. So you survived lesson one of proof by contradiction, the setup. We're on lesson two. To be fair, lesson two reflects more of what the exam questions have shown us. So this is a really, really nice one to follow. You just, for some of these, about two or three different styles, and you just have to practice them to be able to follow the layout. Right, so it says prove that the sum of a rational number and an irrational number is irrational. So what I'm going to do is I'm going to prove that the sum of the rational and irrational is rational. So that's what my contradiction is going to be. Let me just change color on that. It's not prove, is it? So I'm just going to say the sum. Sorry. There. So remember, rational is a fraction. Irrational is like square rooty stuff and and things like that. It can't be formed as like a fraction or as a number. So here, look, so it says here, rational number can be written in the form a over b, where a and b are integers. Irrational number cannot be expressed in that form. Right, so I'm looking at a rational plus irrational is rational. Right, so my rational number, I'm going to use a over b. I'll use the same letters as what's in the pack. I kind of normally use five different letters following on, but this has got slightly different letters, but it's no worries at all. So A over B plus, so I'd use C here, but the pack uses X. And then I'd use D over E here, but I'm just going to use C over D. Right, so what I do is I stick the fractions together. What I want to show is that the left is irrational and the right is rational. And that gives me something that fails. So I want to join the fractions together. Maybe I can write that somewhere. So join fractions. God, my writing is shocking. Sorry, everyone. Um, so I want to get it to a point where I've got an irrational on one side and a rational on the other. And that's when it fails. So x is equal to c over d minus a over b. So if I add them together, I've got bc minus ad over bd. Now here's the thing, if a, b, c and d are integers, then that is also an integer. So maybe I needed to say here, A, B, C, D are integers. It's probably worth it, aren't I? So A, B, C, D belong to the integers. Sneak that in somewhere. It doesn't matter where you stick it. All right. So what I've got here is BC minus AD over BD is going to be rational. So what I've got is an irrational is equal to a rational, which is impossible. You break the world, it would implode. You can't have an irrational number equal to a rational number. It is just physically impossible. So because of this, my contradiction fails. So therefore, the sum of a rational and irrational is irrational. There. So I've got a contradiction. I've set it up. So I was looking at a rational plus irrational is rational. So rational is fractions, irrational is like square roots and special numbers like e and pi. Join them together as a single fraction. But if a, b, c, and d are integers, then that sum bit must also be an integer. So I've got an irrational is equal to a rational. So that bit there, that's where it all fails. So my contradiction has failed, and the sum of the rational and irrational is irrational. So there's another one here, one for you to have a go at. A similar thing, exactly the same idea, same layout. This is rational, that's irrational, can't possibly happen. So therefore, it's done. So that's that question done. So that's come up a couple of times on the papers, and it's quite a nice one just to get your head around. Next. Hang on. There. This is the one we want to follow. So here we go. So we got, so say, 2 classical maths proofs which you need to know. So root 2 is irrational. Right. So if I want to show that's irrational, my contradiction, do it a different color. So my contradiction will be that root 2 is not irrational, so it's rational. So if it's rational, I can express root 2 as a fraction. So root 2 is a over b, where a and b are integers. Belong to the integers. Now, what's important about this specific proof is that they won't cancel down. They're already simplified, so they can't cancel down. So there's no common factors. That's the important bit. If it'll cancel down, if the factors of something else, then it's failed. That's the important bit. It fails if it's from factors, and take factors out that cancel. Right, so I'm going to do a little bit of rearranging. So I'm going to square it first. So 2 is equal to a squared over b squared. So 2b squared is equal to a squared. Now then, this is the bit we don't like because there's a little bit of an assumption in here. So my a squared is even. 2 times anything is even. So because a squared is even, or a multiple of 2, multiple of 2 is probably better writing. So I might remove the word. I'm going to put multiple of 2 here. I'm going to switch to multiple of 2. Because if that was a 3, it would be multiple of 3. If that was a 5, it'd be multiple of 5. So even's nice, but multiple of 2 is probably better. Well, it is better, sorry. The pack used to say even in it. So multiple of 2 is better. Right, so if a squared is a multiple of 2, then a is a multiple of 2. People don't like that step. The only way for a squared to be a multiple of 2 and a to be an integer is if a is also a multiple of 2. So you're kind of really saying a squared's a multiple of 2 squared. Well, there you go. Right. So if A is a multiple of 2, A can be expressed as 2 lots of something else. So now, so if A is 2 lots of something else, then 2B squared is 2M all squared, just subbing the A in 2M to there. So 2B squared is 4M squared. So B squared is 2M squared. So here's my thing now. A squared is a multiple, sorry, B squared is a multiple of 2. I should have wrote smaller. So B is a multiple of 2. And remember this idea that it's got no common factors. A is a multiple of 2, B is a multiple of 2. It'll cancel down, so it fails. Right, so I've got to try and squeeze in my my conclusion here because I got a bit carried away. So trying to squeeze my conclusion in here. So both A and B are multiples of 2. So have a common factor. So my contradiction fails. Therefore, root 2 is irrational. Now that proof has popped up a few times. I can change the number inside the square root. So if that was a 5, it would be multiples of 5 instead of multiples of 2. If it was like a 7, multiples of 7 instead of 2. It could be a cube root as well. I follow the same principle. So if it's a cube root, I'd have a point where A cubed is a multiple of, so so it can fiddle, we can faff with the powers and everything. So here's the exact same one with root 3, but look, see, multiple of 3 now this time. So if that was a multiple of 3, then it's a multiple of 3 there, and it's a multiple of 3. So they both have a common factor, common multiple. So it fails. There you go. So that's one that's popped up a few times as well. So now we have the one that messes with your head. So prove that there are infinitely many prime numbers. Right. So here's what you do. We'll run through it, but I'll have to talk through it in class as well. So it says, so prove that there are infinitely many prime numbers. So a contradiction to that would be that there is a finite number of prime numbers. So the contradiction is that there is a finite number of prime numbers. Right, so think about this. I've got this box. I'm stood there holding a box full of every possible prime number. So what I do is I multiply them together. Now, if I multiply them together, that number is not a prime number because it'll divide through by any of the prime numbers that I've got. But if I add 1 to it, I create a new number that cannot be divided by any of the prime numbers I had before. So essentially, I have created a new prime number. And that new prime number is outside of the box that I'm holding. So I'm holding a box of every single prime number, but I have just magically created a new prime number, which lives outside of the box of every single prime number that I said I have. So that contradicts my statement that I'm holding every single prime number. So therefore, my contradiction has failed, and there are infinitely many prime numbers. It's like that. So here I kind of like imagine I'm holding, every, can't spell, can spell. But here I make a new prime, which is outside of the box. So my contradiction has failed. Right, so let's read what it says then. So that's my idea. So just say again, holding a box with every single prime number. If I multiply all those numbers together, it's not prime. But if I add one to it, it creates a brand new number, which is a prime number, which lives outside of that box that I'm holding. So my contradiction fails. So there are infinitely many primes. The wording, so consider the new number. When you divide n by any of the prime numbers, you get a remainder 1, so it's not prime. So n must either be prime or have a prime factor, which is not in a list of all the possibles. This contradicts the assumption that they're all the prime numbers, and then there's infinitely many primes. I don't think that's ever been on a paper. I could be wrong, but I don't think infinitely many primes has been on. But it's nice to get your head around. So this is like an example that Joel did, where he did it with numbers to show you that if that was your box of prime numbers, they were the only prime numbers you ever had that existed in the world. You multiply them together and add 1, and you get this new number, so which contains prime numbers actually outside of your box that you've got. So there you go. Right, so there's a question for you to have a go at. I just want you to follow it through and see where it went wrong. So let you have a look at that. I think there's another question for you as the last question. Let's have a look at this one. This is a new question, this one. Right, so, here we go. So a miscellaneous proof question. So a student attempts to answer the following question. So given that X is obtuse, use algebra to prove the contradiction. So this obtuse bit is quite important. Right, so I've got greater than or equal to 1. So the negate of greater than or equal to 1 is less than 1. So that's my contradiction. And if you look, they start to square it. So let's follow it through. Absolutely no idea where this is going to go. So let's follow this through from here now. So I'm going to expand the brackets. There. So sine squared plus cos squared is 1. So then I get to a point where that there. Right, okay. So let's have a think about from last year. We know if it's obtuse, that sine is greater than 0 and cos is less than 0. So if this is obtuse, I've got a -2 multiplied by sine, which is a positive number, multiplied by cos, which is a negative number. The left-hand side becomes a positive number, but the right-hand side is a negative number. So that's going to give me a positive on the left and a negative on the right. Now that contradicts it, because what I'm saying is that this is negative. So that's my kind of thing I was trying to say, that this bit here is negative, but it's not. it's positive. The minus 2 sine x cos x can only be positive. But my thing that I've got is saying that it's negative. So let's have a read what it says. So if x is obtuse, sine is positive, cos is negative. So 2 sine x cos x will be positive, which contradicts the statement. So I can't have the positive because it's saying it's got to be less than 0. Can't have a positive which is less than 0. There. So therefore that works. And then I've just got the questions at the end. There. Questions to have a go at. I reckon we're done. Well done.